Hello, calculus students. Where am I? Oh, sorry. Okay. So this is, what is this? Lesson 4.2. And I hope you have seen a beautiful surface behind me. And this is one of those nice surfaces of a multivariable function of x and y. And you too can draw a picture like this if you download a free app. Just look for any kind of a 3D graphing app or a 3D graphing calculator, and you will be able to do something like this. And if you cross this surface with, z is equal to 0 or 1 or 2 or whatever, then you can have a contour lines or what we call level curves, okay? So this is section 4.2. And so the fundamentals of vector value, the multivariable functions are done now. And so next we will go into limits and continuity. And so that's what this lesson is about. So let's get started on limits and continuity of multivariable functions. Section 4.2, limits and continuity of multivariable functions. All right, as I always do, I would like to start this section with what you already learned back in Calculus 1. So what is a limit? Okay, so you have probably seen two definitions, one casual and informal, the other one more rigorous and mathematically precise. The first one, maybe I should just write this to start with. Recall, so here's the first definition or quote unquote definition of the limit that you probably learned. We say the limit of f of x as x approaches c, as shown here, is equal to L if and only if, any definition, because it's a defining characteristic, you should say if and only if, okay? It should go both directions, right? If and only if, as x approaches c, and an important point here, from both sides or from both directions, that f of x, which is y, approaches L, okay? So we say y gets closer and closer to L as x gets closer and closer to to C. And again, an important thing here, without x being exactly equal to C, we don't care what happens when x is exactly equal to C. So for all we care, or all we care about this, we don't have to have this thing here. Now this is, this could be filled, but it doesn't have to be filled. It could have an empty hole there, and the limit of this function, the limit of f of x as x approaches c, is still L in this picture, even if there's a hole, okay? So it doesn't have to be continuous to define limit. In fact, f of c in this case is not even defined, right? F of c has no value of y because there's a hole. But even then, as x approaches c from both directions without actually becoming c, if y gets closer and closer to this value L from both directions, we say the limit of f is L at x is equal to, so as x approaches c, okay? So this is the informal definition. And so we will call this, actually, informal definition is not a definition as far as mathematics is concerned, but it is intuitive, okay? This is the part, this is the intuitive. This is the definition, or this is the description that we can understand. All right, so here's a more precise definition, mathematical, more formal. And so this one involves two Greek letters, which sort of characterize one's knowledge of calculus. If you talk about epsilon and delta, and if a person has no understanding what you're talking about, that person is not a calculus student, right? So we say the limit as x approaches c of f of x is equal to is L if and only if, and maybe some of you can do this in your sleep. That's a noble ambition. I can probably do that myself. If and only if for every epsilon greater than delta, there exists a delta, lowercase delta, greater than 0, such that whenever x minus c, the absolute value of x minus c is equal to or less than or equal to delta, then the difference between f and x and L is less than epsilon. This is not completed yet. I will complete this in just a second. All right, so the idea is, and as I mentioned this before, just imagine having the same picture as above. Okay, the problem with this first intuitive definition is, although it is easier to understand, it's not precise enough. We can't really, in mathematics, be precise and say things like get closer and closer to. So the idea is to make it, in order to make it more precise, we introduce this epsilon. Somebody will challenge you with a small epsilon. Let's say epsilon is 0.001, okay? And so that's like a tolerance. Can you come up with a delta, all right? Let's say you're giving a very small epsilon, and then the question you are asking is, can you make delta so small that as long as x is within this interval from c minus delta to c plus delta without being actually equal to c, somewhere around here, as long as x is within this interval without being equal to c, then can you guarantee that my y value will be within this reasonable tolerance between L minus epsilon and L plus epsilon? And can you find a delta for every epsilon I give you? And if you can show me that you can come up with a delta for every epsilon I give you, then we say that the limit of f at c is equal to L. Okay, and so it turns out to be a very clever definition. I don't know who came up with this. I think it's Weierstrass. But anyway, this is an incredibly a critical and important definition in the fundamentals of calculus. Right now, the thing is, I said we don't care what happens when x is equal to c. Again, x could be sort of having a hole at this point. So we don't want to say x is anywhere between this point c minus delta and c plus delta. We want to make sure that x is not equal to c. And so in order to do that, I'm just going to add this one little thing here. We make sure that x minus c, the absolute value of x minus c is positive, which means it's not 0, which means x is not equal to c. So what this says is, can you find, for every epsilon, can you find a delta so that, okay, as long as x is within delta distance of c without x equals to c, okay, then, and whenever this happens, then f of x is within epsilon units of L, okay, and so if this condition is satisfied, we say the limit exists. Okay, you don't need to know, I'm not going to ask you this on your test or anything, okay? And so the important thing here is this thing here, you have to be able to do this from both directions. Why say both? Okay, so we have this old joke, that there's a little college and the wildfire came and burned down their entire campus and their library, and both books were burnt. What do you mean? Like, yeah, the joke is that when you say both books, the implication is that the library only had 2 books, right? So when you say both, we are implying that there's only two, or there are only 2 ways to approach this C, from the right and from the left. Okay, so now for our calculus 3, if f of x, y, or f of x, yeah, let's just say f of x, y is given. Okay, now it could be, you may have a third variable x, y, z, but we will not worry about that right now. If f of x, y is given, here's what we say. The limit of f of x, y as x, y approaches a, b is equal to f, if and only if. All right, so now the idea is to make sure that we say exactly the same thing here, right? So the idea is this. We can have the first intuitive definition, description, and then the second one, more rigorous definition. All right, so here we go. For the multivariable function f of xy, here is the definition or definitions of limits. Okay, so we can say in one way that as xy approaches AB from not both, but from any direction. Remember, because now we have infinitely many directions along which xy can approach AB. So as xy approaches AB from any directions without actually becoming AB, okay, without xy equals AB. As xy approaches AB from any direction, f of xy approaches L. All right, so that's corresponding to our first definition, just like this one here. And hopefully it makes sense. Maybe I should draw a picture of this. Okay, so here's a picture of a multivariable function f of xy, and we're approaching this point AB, and we allow this point xy to approach AB from any direction like this, okay? Even along a curved path if possible, right? Any direction, in any way, if xy is approaching AB and get closer and closer to AB, what's happening with the value of f of xy? Well, let's say at f of AB is, maybe there's a hole, but if there were no hole, this value is L. Okay, we want to say the limit is L if as long as or as xy approaches AB from all directions, f of xy approaches this length, this height, or this z value L from all directions. Okay, now L is a real value, and so we don't have to worry about all directions, but we assume that for this to be true, as long as xy is approaching AB in any directions or fashion, then f of xy approaches L. All right, here's a more precise definition. We say, again, let's just highlight this. We say the limit of f of xy as xy approaches AB is equal to L if and only if, okay, so for every epsilon greater than 0, there exists a delta greater than 0 such that whenever, now this is a tricky part, right? Whenever the distance between xy and AB is less than delta and not equal to 0. Of course, equal to 0 means xy is equal to AB. We want to avoid that. Not equal to 0, but it is less than delta units away from AB, then f of xy minus L. Remember, these are real numbers, so I can actually do subtraction and define the absolute value of this, and that value has to be less than epsilon. Okay, so again, for every epsilon, can you find this delta? And so the picture I drew here, you have this AB, and then you have this round ball with a radius of delta. That's all the points xy, such that, as I said here, the distance between xy and AB is less than delta and not equal to 0. Okay, so xy could be any of these points inside of the delta ball or delta neighborhood of AB without actually being AB. For each of these xy, f of xy has to be within epsilon distance of L, right? So that's what the definition means. Okay, so that's the theoretical aspect of it. You will study more if you take an advanced math class in your 4-year university called real analysis or advanced calculus or something like that. But for our purposes, you do not have to worry about epsilon and delta, but I do want you to know, as a serious student of mathematics, you should be familiar with the epsilon delta definition of limits. Okay, so good news follows, okay? Good news always follows epsilon delta. Good news is that limits are like my children, well behaved. I'm not sure about the last thing I just said. Limits are well behaved. Okay, so what that means is the limit, and you know what this is, limit of f plus g. Okay, as xy approaches a, b, what is that? Okay, this is the limit of f as xy approaches a, b, plus or minus the limit of g as xy approaches a, b. That's cumbersome to write, but that's what it is. Right? So what does it say in English? It says basically that the limit of a sum is the sum of the limits, and the limit of a difference is the difference of the limits. Okay, and it even works with the product and the quotient and everything. All right. So all this really says, for our practical purposes, is that if you can plug in x and y values, okay, then do that. And then it'll give you the right limit, okay, just by plugging in. You remember this? Yeah, I mean, you remember doing things like this on your Calculus 1 homework, right? Similarly, this is true for the product and the quotient, as long as the denominator is not equal to 0. Okay, so these will say, and like this one would say the limit of a product is the product of the limits, and this one is the limit of a quotient is the quotient of the limits. You can almost write a song with those 4 lines as the first 4 lines of your lyrics, right? And so here is even better news. All polynomials. You know what polynomials are, right? X squared, y squared, x cubed, y cubed, and all the combinations. Every exponential function. And if I'm bold enough to say this, every rational function wherever it's defined, every radical definition wherever it's defined, every log, including the natural log, wherever they are defined, these are all continuous. Now, I don't want to say, for instance, rational includes 1 over x. I don't want to say 1 over x is continuous everywhere. That wouldn't be true. But you'll say these are all continuous wherever they are defined. Okay, so if you have a strange log function, right? Whatever, log base 25 of x or something. Well, that function is continuous everywhere where x is positive, okay? Because log of a positive number is defined. So this means you can plug in to find your answers, okay? And in that regard, this is very nice. So let me give you an example. And of course, we will spend a lot of time talking about what happens if you can't plug in the numbers. And of course, that's really the main part of this lesson here today. All right, so let's say you have a xy, find the limit. As xy goes to 1, 1 of xy minus e to the x plus y all over square root of x plus 3. Okay, so can you figure this out? Yeah, because xy is a right, so let me just go ahead and do this. Maybe a light color. This is a polynomial. Okay, this is not a polynomial because you have e to the whatever. That's an exponential function, and this is a radical function, right? And so what we have is a polynomial, polynomial minus exponential. It's continuous minus continuous, and the difference of 2 continuous functions is continuous, divided by another continuous function wherever the function is defined. And when x and y are close to 1, 1, all of these partial function parts are defined, right? So all you have to do is just plug it in. 1, 1 minus e to the 1 plus 1, that's 2, divided by the square root of 1 plus 3, which is 4. So this is 2 minus e squared over 2. That's 1 minus 1/2 of e squared. No problem, right? I mean, this is easy stuff. It's great, right? And so I actually didn't tell you what we mean by continuity because that is yet to be defined. But the idea of continuous means that when the function is continuous, then as you will see in just a second, then you can plug in the value to find the limit at that point. Okay, so let's go ahead and give you, I'm going to give you the definition of that word, continuity. We say f of xy is continuous at a single point, AB. Okay, now do you remember the definition that you learned in Calculus 1 for continuous function? A function is continuous in an interval if it's continuous at every single point of the interval. Well, duh. What does it mean for a function to be continuous at a single point? Okay, and we had actually three, I think you had three parts of it. The first is that the function has to be defined at that point. Okay, now corresponding to that is f of AB exists. Okay, i.e. f of xy is defined. It doesn't have the zero denominator, for instance. F of xy is defined at AB. So this has to be true. Number two, the limit must exist. The limit is written this way, not AB here. The limit of f of xy as xy approaches AB must exist. Okay, and the third and the most important part of that is that these two numbers have to be equal to each other. So the limit of f of xy as xy approaches AB is equal to f of AB. Now, if you look really carefully at what I wrote here, this really is the key definition, right? I mean, you can ignore the first two, because if these things didn't exist, then the last statement wouldn't make sense, right? Because, I mean, the right-hand side is number one, the left-hand side is number two. If this fails or this fails, then number three is meaningless. So you could just say definition of continuity is this number three, okay? So why do we even list one and two? Well, just for completeness, okay? And in Calculus 1, you learned a threefold definition with these three components. You know, the first one, the existence of the value of the function at the point, and the existence of the limit at that point, and the fact that they are equal to each other. Okay, so, and this actually tells you, the last one tells you then, what is the limit of f at AB if f is continuous? The answer, f of AB. So plug in whenever it's possible. So it's only when you cannot plug in because you know, something happens, like an undefined term appears or something, that you have to be clever to figure out what the limit is. And the rest of this lecture will probably be concerning or be involving that question I just mentioned. Okay. All right, so with that in mind, let me give you an example of this. What do you think the limit of this function is, y over x, as x and y approaches 0, 0? Okay. The answer is not 0 over 0. This is probably the worst thing that you can write. Okay. Another bad thing you can write is undefined because it's 0 over 0. Okay, so these are really bad answers. In fact, you will not get, as long as you're my student, you will not get any partial credit for writing 0 over 0. In fact, I may turn you in for speaking foul language in class when you put 0 in the denominator. Okay, you don't want to say undefined because this limit actually is not quite undefined. I mean, I know what you mean when you say it's undefined because you cannot plug in 0, but that's not the reason why the limit does not exist. There is a reason that the limit does not exist, but that's not because this is undefined. Remember, the function can be undefined at a particular point and the limit can still exist. That is exactly what was happening in this case, right? The limit where f of c is empty. There's a hole, but the limit still does exist. So just the fact that f of xy, f of 0, 0 is undefined does not mean that the limit does not exist. Okay, so make it very clear that the fact that this gives you an undefined term, or this gives you something over 0. That's not the reason why the limit does not exist. So think about how you may approach this problem, and we'll come back to it in the second portion of this video.